Hey there, well, welcome back. We are starting our last couple of videos here that have to do with acid-base reactions. This particular one, we're going to be taking a look closer at the concept of what pH is. Now, everybody has heard of what pH is, and kind of knows that it's sort of a weird little scale. Like, why does it go from 1 to 14 and not 1 to 10? And the whole purpose of this particular video is to kind of connect maybe what you've heard about pH with that concept that we covered in the last chapter, which was equilibrium, because they are strongly related to one another. And that was the whole reason for me giving you that whole background piece on equilibrium and what that is, so you'd have some more understanding about what pH really is and what it measures and why. So that's kind of what we're going to do in here. The mathematics of pH is actually a really simple little equation, which I'll get to here in a little bit. But kind of understanding what pH is a little bit trickier. So first thing is to think about kind of how water reacts and how water behaves. Sorry, get my pen going here. How water reacts and how water behaves in response to other things, because this actually gives us the basis. It's water's behavior that actually gives us the basis for pH, not the acid or the base. Believe it or not, it's both, but it's how the acids deal with water and how bases deal with water. So the first thing is this idea that water is an amphoteric substance. That's a really weird word, isn't it? Amphoteric. This is based on the earlier work that we did, that when you have something like HCl, which is an acid, that this is going to act like a proton donor. And so when it's done, you're going to get that. It's conjugate base. Conjugate base. And then you're also going to get this thing is going to have to receive that proton. If HCl is a proton donor, then water has to be the proton receiver. And we get the formation of that hydronium ion, or just written as H+ is fine. Again, either way is correct. This H3O hydronium ion it's more realistic in terms of what it's actually existing like. But again, a lot of times we tend to write it as H+, and they're both kind of correct in this sense. So in this case, water is acting as a base. But what happens when we put a strong base in there? Now, this is ammonia, NH3. And in this case, this acts like a base. So that means our water here is going to be acting like an acid, where our water is our proton donor and our base here is the proton receiver. So we actually get this, ammonium ions and OH minus. So this here, when we kind of switch their sides, this becomes our conjugate acid and this becomes our conjugate base. So again, amphoteric is this right here, that water has the capacity to act as either a proton donor or a proton receiver, and in fact, it acts like both. That's what amphoteric means. And this is actually really important to understanding acid-base behavior and how water is capable of reacting both ways. It's definitely an unusual substance that it has. And in fact, if we kind of go one step further, water can act like both an acid and a base when it's by itself. So here we've got water acting in one sense like a proton donor and in one sense like a proton receiver, right? You've got both of them on there. And this is called auto-ionization, that there is a very small amount of this that does happen from time to time naturally, right? Most of the water likes to be in regular water molecules like we're used to, literally H2Os. But it will, under certain circumstances, just occasionally fall apart. Auto-ionize, that's the term for it. And so when we create an equilibrium expression for this, we would still do products on the top and reactants on the bottom. This is called the dissociation constant, right? In the last chapter, we talked about the equilibrium constant, KEQ. Well, the water cases is specifically important enough that we call it KW, because there's this really special case. And when we do equilibrium expressions, remember, we always kind of do this kind of thing where we do products up here, and then we do reactants down here, REACT, and these are both in molarities, right? Square brackets. So we would kind of do the same thing for this one. When we talk about the auto-ionization of water, we do this, the concentration of the products, hydrogen ion concentration times hydroxide ion, over the concentration of water. Now there's something we're going to talk about on the next slide here, which is a little bit awkward. When we write equilibrium expressions, there's some things that we never include. I think it's on my next page. Let me pull it out here. Hold on. And it's up at the top here. When we write equilibrium expressions, we never include liquids and solids. We really only include gases and solutions, things where their concentrations are variable. A liquid is always 100%. Its concentration is like infinite because it's pure, right? Same thing with a solid. It's pure. It's only when it's dissolved in water that we have a kW or an equilibrium expression that can work. So what we would normally write is this: kW equals hydrogen ions times hydroxide ions, right? The product of those over the concentration of water. Well, the concentration of water, this is a liquid. Concentration of water is pure water. This is basically equal to 1. And so this ends up going away. It's just not in that kW expression, that self-ionization constant. So what we get is this right here. There we go. There's like our equilibrium expression for what water does when it self-ionizes. And it turns out we know the value for this. Here it is right here. It's a super small number, 1 times 10 to the minus 14th molarity, its concentration. But in terms of the amount of water that does this, this tells you that, yeah, for the most part, water stays as water, and only a very tiny, very, very, very tiny product amount of stuff actually ionizes, is in actually this H plus and OH minus form. And you also know further that if it's neutral, plain water is neutral, right? That we know that the concentration of hydrogen ions and hydroxide ions has to be equal to one another. So how do we kind of mathematically solve this? If I know that this is equal to X and this is also equal to X, and those two times each other equals this, 1 times 10 to the minus 14th, we can do a little bit of math on there. I'm not trying to kill you guys with logs and exponents and all this kind of good stuff. It turns out there's actually a very simple little equation for this. And this is the same stuff that I had on the other screen. I'm just kind of writing it in a way that's not my handwriting. So here's our ion product constant right there, or our kW, where we know that water, the product of those two ions, is always 1 times 10 to the minus 14th. That is always true regardless of what's in it. That's a tiny number. And again, if these two equal one another, that means that each one of them has to be equal to that. The concentration of hydrogen ions and or hydroxide ions in pure water is 1 times 10 to the minus 7th. 1, 2, 3, 4, 5, 6, 7 molar. It's a tiny, tiny, tiny amount, okay? So this is important. That 10 to the minus 7th thing becomes an important value for us. So a couple things that you do know about this. And again, just as a reminder that there's some things that you know. You know that if we have these two values, what acidic and basic is. You know that if hydrogen ions are more concentrated than hydroxide ions, they're acidic, sorry. If you know that the hydrogen ions are less concentrated than the hydroxide ions, they're basic. But we do know that the product is always kW. So now what's funky about this is the way that the math works, is that if we have that times that again, 0.0000001 molar, okay? If this is hydrogen ions and this is hydroxide ions, for example, then the product of this is 1 times 10 to the minus 14th. Okay, but what happens if we start to change those values? It turns out that we're going to typically deal with this by decimal places. And this is kind of the nice cheat that we can do on this. And again, I know this is a little bit weird, but you can play with your calculator and figure it out if you want to. If this is 1, 2, 3, 4, 5, 1, okay, this is 1 times 10 to the minus 1, 2, 3, 4, 5, 6. This is more concentrated. I know it doesn't feel like it, right? 1 times 10 to the minus 6 is more concentrated times 1 times 10 to the minus 7th. That means that I now know the concentration of this. 1, 2, 3, 4, 5, 6, 7, 8. If one goes up by 10 times, the other one has to go down by 10 times. And this is kind of a really weird thing, that if that's the hydrogen ion concentration, then the hydroxide ion concentration is 10 to the minus, 8. Notice what the exponents add up to. 10 to the minus 6 times 10 to the minus 8 is 10 to the minus 14th. The exponents add up to 14. They always do. It's a weird thing that happens. And again, this has to do with how logs work and all that kind of stuff. So I'll show you how we mathematically deal with this. But it's a really cool little mathematical tweaky thing that we can use. The product of our two concentrations is always kW. So if I know one of the two concentrations, let's say if I know that hydrogen ion concentration is 0.00023 or some random value, all I need to do is solve in this equation to figure out what my value of my hydroxide is. I would say my concentration of hydrogen ions, 0.0023, times the concentration of hydroxide ions has to be equal to 1 times 10 to the minus 14th, always. So you can kind of plug those in and play around with one. When you know one, you know what the other one is, because the product is always a constant. So what does this mean for us? Well, here's how we make it easier. Rather than dealing with all these little teeny tiny numbers, we're going to use the log button on your calculator. And it's actually the one that says log. There it is right there. You've got several different ways to do that, but there's always a button that says log. And here's the nice thing about logs. What logs do for us, okay, what logs do for us in this particular circumstance, this is kind of cool, is that a log has everything to do with the exponent in these things. That's what a log means. It's a 10 to the scale. So what's kind of cool is if you were to actually go do this number and put it in your calculator and take the log of it. If I literally take the log of 1 times 10 to the minus 7th and hit equals, if I hit equals on that, and again, make sure you use your scientific notation. Make sure you're using the EE button and not the long way button. Again, this is critical. If I do this on a calculator, the answer to this is -7. If I did the log of this, 1 times 10 to the minus 3, the answer to that is -3. Try it. The log of this number, log of 1 times 10 to the negative 19th, is going to be -19. That's what the log does. This function right here cancels out all of this function, and it outputs the exponent. That's what the log function does. It's kind of cool for us. So what we do is we make a little formula out of it. And see how there's a negative sign here at the front? What that means is I now take this and turn it into a positive value, right? If I do the negative log of 1 times 10 to the minus 7th, then my answer is 7. Or the negative log of 1 times 10 to the minus 3, then my answer is 3. So this is what pH is. pH, and again, the P here actually stands for the power of, as in exponents power. That's what it's referring to, not like, Power Rangers, but the power of hydrogen. What this function allows us to do is it allows us to give us insight into what the exponent is. And that exponent tells us how concentrated it is. So if you've got 0.0001 of hydrogen, like this, if it equals that, that would be its 1 times 10 to the minus 4 would be our hydrogen ion concentration. If I take my log of that and turn it negative, then that means that my pH of this substance is equal to 4. That's acidic. Well, why is it acidic? Well, because 1 times 10 to the minus 4th, relatively acidic by comparison. Remember what our baseline is. 1 times 10 to the minus 7th is our baseline neutral situation right here. This is the concentration of hydrogen ions in a neutral solution. So the negative log of 1 times 10 to the minus 7th is equal to 7. That's what that pH means. If I have something acidic like this one, 1 times 10 to the minus 4, that's a lot more concentrated, right? 2, 3, 4, 5, 6, 7. That's 1 times 10 to the minus 7th. This is 1 times 10 to the minus 4th. 1, 2, 3, 4, right? This is, if these were hydrogen ion concentrations, this is way more concentrated than this one is. And so the pH of this one, 1 times 10 to the minus 4th, is going to be pH of equal to 4. So the negative log of 1 times 10 to the minus 4th, for example, is going to be 4. If I've got a basic solution, now I have to go even smaller in my value, not more concentrated, less concentrated, like 0.000001, 2, 3, 4, 5, 6, 7, 8, 1, something along those lines. This is 1 times 10 to the negative 9th. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? That's even a smaller concentration of hydrogen ions. If I take the negative log of this, the negative log of 1 times 10 to the minus 9th is equal to 9. That's a basic solution. So what this is telling you, this negative log, what the pH is telling you is indirectly, it's telling you the hydrogen ion concentration. That's what pH tells you. So again, it's the number of zeros, I guess, in front of the 1. So something that is a very strong acid with a high hydrogen ion concentration, like that, which is way more concentrated than this, that is a pH of equal to 1, right? So the higher the hydrogen ion concentration, the less decimal places you have. So when you take the negative log of that, that becomes closer and closer and closer to 1 as you do it. So when you're doing this stuff, again, there's a couple other little things that pHs aren't always that easy a number. So I just want to kind of show you how we kind of go the other direction. But again, the whole idea about this equation, it's really kind of a plug and chug, but then there's a little bit of trick with using your calculator. So we want to find the hydrogen ion concentration if I know what its pH is. I would literally plug it in. 3.15 is equal to the negative log of the hydrogen ion concentration. I got to figure out what that is. Be careful with your algebra on this. Because of the log function and what you're trying to do, you got to be a little bit careful how you type it in. So order of operations is important. So you do negative 3.15 equals the log of hydrogen ions. And then in order to undo this, you would do this, inverse log. Again, it's going to be it's like a second function, right? Like on one of these calculators, my log button is here. I got to do the second button first. So it's the inverse log of negative 3.15. By the way, the inverse log, the actual formula for that is, the function is this, 10 to the x. That's the name of that function. This is called inverse log. That's the name of that particular thing, 10 to the x. So again, when you see it on your calculator, that's what you're looking for. But it's the second button, or the inverse button. So when I enter this in here, the inverse log of negative 3.15, I go, turn my calculator on, second in log, and then I do negative, make sure you're using the negative sign, not the subtract sign, 3.15, and then I hit enter, and then I get a crazy number like that. Okay, I know it's kind of hard to see what it is. So let's take a look at it. It is 7.07, 7.079, 4, 5, and some more, times 10 to the negative fourth. Now, wait a minute. How does this make sense, right? What? Hold on. This doesn't seem to work. Okay, so now because you're taking the inverse log, things are a little bit strange. If I did the negative, or the inverse log, inverse log of negative 3, not 3.15, but 3, I would get a value of 1 times 10 to the minus 3. That's what that would tell you. Hold on, inverse log of negative 3. Literally gives me the exponent, okay? Again, if I take the negative log of 3, I get 10 to the minus 3, or 0.001. But I took the inverse log of a number, not just 3. I did 3.15, right? That's where this is giving you a weird kind of value to it. This is really close times to 10 to the negative 3. In fact, it's really close to 10 to the negative 3. This is 0.0007, which is really close to 0.001. This is 10 to the minus 3. This is almost that. So again, the numbers look really different, but they're actually very similar in terms of the true value of what these things are. Okay, last thing I'm going to say, the second to last screen here. Last thing I'm going to say, sig figs with this is really weird. Here's our note about sig figs on here. Okay, sig figs is a little bit strange because of the way that the inverse logs work. Okay, I know it's going to drive you nuts. This is where you actually get the sig figs. That gives you the exponent, or the number of decimal places. That part gives you the sig figs. I know it hurts. So I would literally write this as this: 7.1 times 10 to the minus 4 molarity is equal to my hydrogen ion concentration. That would be the final answer for this. So what is the hydrogen ion concentration of a solution with a pH of 3.15? I would plug my numbers into my equation. Here they are. Be careful with your order of operations. And then for sig figs, you're looking at whatever's after the decimal place. So 2 sig figs in this case. The 3 does not count. The 3 actually gives you the number of decimal places. It actually turns out to be in that part of the exponent number. It's weird. I know. I'm sorry. All right. Last bit. When we were doing one last other thing in terms of, actually, I guess it's 2. Yep, this is my last screen. There's one other extension that we can do to this. We talked about pH, and everybody knows about pH. But pH has a brother, pOH, which is the power of hydroxide ion concentrations. It's done the same way. You can see the formulas here are exactly the same, with the exception that one's about hydrogen ions and one's about hydroxide ions. So keep that in mind. Now, here's the 2 little bits of shortcut. If you're trying to deal with hydrogen ions and hydroxide ions, we know that due to the ionization constant of water, that the products of our two ions is always equal to 1 times 10 to the minus 14th. So once you know a hydrogen ion concentration, like we did in that last one, you could plug it into this equation and determine the hydroxide ion concentration. So I said from our last problem, we knew that our hydrogen ion concentration was 7.1 times 10 to the minus 4. So if we have this one, 7.1 times 10 to the minus 4, we can plug it in here and know that this is true, and we can figure out what our hydroxide ion concentration is. That's certainly one way to figure that out. Another nice little thing that we can do, because of the way that logs work, and again, trust me, you don't want me to derive this, but we can. One of the fun things is, because we're taking the negative logs of all of these things, if you go through and do that on every one of these, negative log of this, do the negative log of this, and do the negative log of this, what we end up with is this. It's kind of nice. The pH plus the pOH. I know there's a multiple in here. Trust me, it works, okay? That's not a mistake. That's correct. That when I know the pH of something, the pH plus the pOH will always add up to 14. It is a direct algebraic derivation from this based on log rules. So trust me on this one, like I said. So if I knew from my last problem that my pH was 3.15, that it was 3.15, then the easiest way to find the pOH is just to subtract. 14 minus 3.15 gives me a value of our pOH would be 10.85. Okay, that would be our pOH. And then I could use this equation up here to figure out what my hydroxide ion concentration is. They both work. They do the exact same thing. So whichever one you prefer. You can either plug in your raw hydrogen ion concentrations here and then solve for OH. Or if you know what the pH is, then you can rearrange this equation. You use pH plus pOH equals 14, solve for your pOH, and then you can plug it back in this way. So again, when we're dealing with that concept of equilibrium in acids and bases, it has to do with the ion product constant of water, which is the fact that we've got right here, our Kw. It's an equilibrium. Even when we put acids or even when we put additional bases into there, the water will adjust. It's amphoteric and will always achieve a new equilibrium so that the ion product constant is always 1 times 10 to the minus 14th. And then we can do some simple log functions. There's our little simple equations to turn those into a little bit easier numbers to deal with. So that's really all pH is. pH is just a simple way of figuring out what our hydrogen ion or our hydroxide ion concentrations are through using a logarithm formula to give us a nice, easy output, because people really like whole numbers way better than they like scientific notation. So there you go. That's kind of our moving around what pH is, your simple formulas for pH, how it relates to equilibrium, and how the pH balance of pH and pOH always adds up to 14. So there you go. I hope you got something out of that, and I will see you in class next time.